In this lesson, we're going to explore big idea number 1 and discuss energy changes and how you describe them quantitatively. And we'll be looking at learning target number 2. So by the end of this lesson, you should be able to determine an enthalpy change experimentally using a calorimeter and discuss the sources of error involved. A calorimeter is a piece of lab equipment that insulates the system so that the energy lost or gained can be measured. A coffee cup calorimeter is the cheapest version, but still offers very accurate results. Calorimeters surround the system with water, which we can easily track the temperature of using a thermometer. We can use the temperature change to calculate the amount of heat the water absorbs or releases during the reaction using the following equation. Q equals mc delta T. Now, I often put a subscript W here to remind myself that I can only plug in information about the water. Q is the energy change of the water in joules. M is the mass of the water in grams. You usually get this by taking the total volume in your system in mils and changing it to grams because the density of water is 1 gram per mil. The specific heat capacity of water is a constant. It equals 4.18. That tells us that 4.18 joules are required to raise 1 gram of water by 1 degree Celsius. And then the delta T stands for the change in temperature of the water. Now, you can use Celsius in here because this is change in temperature. It doesn't matter if you use Celsius or Kelvin because you're subbing in the change. Since the water is the immediate surroundings, QW, or the energy change in the water, can be changed into the energy absorbed and released by the system using the first law of thermodynamics, the law of conservation of energy. All we have to do is flip the sign. Remember that enthalpy change is reported in kilojoules per mole. Therefore, we can calculate enthalpy change by using the equation delta H equals the energy change of the system divided by the moles of the limiting reactant. Here's an example. If we take 50 ml of 0.3 mole per liter copper sulfate solution and mix it with excess solid sodium hydroxide in a cup calorimeter, the temperature of the water decreases from 24.6 degrees Celsius to 21.4 degrees Celsius. Determine the enthalpy change. Once you find the enthalpy change, you should be able to communicate it using a thermochemical equation or, if asked, an energy diagram. Let's start this example by writing a balanced chemical equation. We're going to mix copper sulfate and sodium hydroxide together. This is going to be a double displacement reaction, giving us copper hydroxide and sodium sulfate. Now, to balance this equation, you need 2 sodium hydroxides, and to complete the reaction, we need to include our states. I know from the question, since the temperature of the water decreases, that this reaction is going to be endothermic. So that means energy is going to come from the water and enter into our chemicals. I can calculate how much energy the water releases by using Q equals mc delta T. Now I can only plug in information about the water in my calorimeter. The first term is the mass of the water. If I look at the question, I have 50 ml of fluid in my calorimeter. That translates into 50 grams of water using the density of water equaling 1 gram per mil. I times that by the specific heat capacity 4.18, and the change in temperature of the water, it goes down by 3.2. So I have to have a negative term introduced there. that means the water lost 668.8 joules of energy. Or, if I convert that into kilojoules by dividing by 1,000, 0.6688 kilojoules. Now, to find the energy change of the system, all I have to do is flip the sign. Whatever energy the water lost, my chemicals gained. That follows the law of conservation of energy. Now, in order to find delta H, I need to take the energy change in my system and divide it by the moles of the limiting reactant. The question says I have excess solid sodium hydroxide. That tells me that my copper sulfate is the limiting reactant. So I need to find how many moles of CuSO4 I used. It's a solution, so if I take the concentration and I times it by the volume in liters, that will give me 0.0150 moles. So to complete the question and find the delta H, I'm going to take my energy change of the system and divide it by the moles of my limiting reactant, and that gives me my enthalpy change in kilojoules per mole of copper sulfate. The question also asked me to write a thermochemical equation. Well, I have that 3/4 done because I wrote the balanced chemical equation. All I need to do now is include this enthalpy change in my equation. Again, because it's positive, it's showing me that this reaction is endothermic. So that means that I have to write the energy on the reactant side. Now, this is in kilojoules per mole of copper sulfate. So I have to look and see what coefficient I used to balance my equation. There's a 1 here. That means my number does not change. I'm going to put 44.6 kilojoules. But let's say, for example, there was a 2 there. For every 1 mole of copper sulfate that gets reacted, I get 44.6 kilojoules of energy inputted into my system. So if I had to balance this reaction with a 2, then I wouldn't write 44.6. I would write 89. So here's my completed thermochemical equation. Pause the video and try out example number 2. Now this example doesn't tell you which one is the excess reactant. You need to find that for yourself.